really, let's look at something like this. Co-16B, date is 6th of February. So let's say we have, sure, the integral of sine of x times cosine cubed x. Oh, let me do this real quick. This is a great example of how you could actually pick u to be either trigonometric function. You could pick u to be sine, or you could pick u to be cosine. But there's almost always a better choice. Here, the better choice is going to be letting u equal cosine, because if you think about this, this is sine of x times cosine of x raised to the third power. And so letting u equal the thing that's stuck inside another function is almost always the better choice. So here, I would choose to let u equal cosine of x. Du, the derivative of cosine, would be negative sine of x dx. I don't have a negative, so I'm going to adjust. I'm going to say that negative du is equal to sine of x dx. And I'm going to rewrite this. So I like writing it so the stuff that wants to be next to each other is, meaning I would like to view this as the integral of cosine of x cubed times sine of x dx. And then I'm going to go ahead and replace them. I have the pens. There we go. So sine of x dx, that's going to be equal to negative du. And cosine of x cubed is going to be equal to u cubed. Now be careful when you write this. We definitely don't want to write it as the integral of u cubed minus du, because we're not subtracting here. It's u cubed times negative du. I would skip writing it this way and put the negative out in front, or any constant multiple out in front. So I would definitely write this as negative integral of u cubed du. Anti-differentiate, get negative u to the 4th over 4 plus a constant. Trying to make your u's not look like 4s. It's always my issue. And then finally, sub back in what u is equal to. We get negative cosine of x to the 4th power all over 4 plus c. Or written probably more normally, negative cosine to the 4th of x all over 4 c. Either way is fine. This is the more kind of typical notation, but either way is okay. Let's look at some other trig ones, because trig does come up. They can be a little bit challenging. So let's actually talk about the integrals of the trig functions. So I know we've talked previously about all the ones you should already know. Like we should know that the antiderivative of secant squared is tangent, because we already knew that the derivative of tangent is secant squared. And that list kind of goes on. But then we might ask something like, what is the antiderivative of tangent? And that is something you're going to be expected to know. At least I know one of the classes already covered these. I don't know if both of them have. But the way we do this is by doing another u sub. We're going to rewrite tangent as sine divided by cosine. This one always feels a little bit tricky in that everyone would really, really rather choose u to be sine, because the derivative is cosine. Whereas if u is cosine, the derivative is negative sine, and feels like the better choice is the one where you don't have the negative. But the problem is if we pick u equal to sine, your du is cosine of x times dx. And we don't have cosine of x times 6. We have 1 over cosine of x times 6, which is a completely different animal. So here, just like in the other one, we want to choose u so that this u is stuck inside some place. Here, cosine is stuck in the denominator. And that's definitely our motivation for picking u equal to cosine over picking u equal to sine. You should do the rest of this. Find du. Rewrite the interval in terms of u. I'll give you a minute and a half. Welcome to those just joining us on Zoom. We're doing the integral of sine over cosine via u substitution. So go ahead and try letting u equal cosine and see what happens. Let me put the attendance form in the chat for you all as well. There you go. Hopefully your answer has a logarithm in it somewhere. If you're not getting a natural log in your answer, then you should go back and look again. So that helps. All right. Then all the time I said you would get. So we let u equal cosine, just like in the previous problem. Our du is negative sine of x times dx. And since I have a sine of x times dx, I'm going to bring the negative over here and say negative du equals sine of x times dx. If you prefer, you can do the thing where you say dx equals negative du divided by sine of x. Not how I like to do it, but that's okay to do it that way. So then rewriting this, so watch here, I see that and I rewrote this so that I could put the sine x times dx right by itself, because I know that's going to turn into negative du, and then the 1 over cosine is going to turn into 1 over u. And then when I write the next integral, I'm going to put that -1 coefficient out in front. I wouldn't normally write -1, I would just write negative, but it's fine to write -1. And then you got the integral of 1 over u du. And the antiderivative of 1 over u is the natural log of the absolute value of u. We get a plus c. And finally, replacing u with what it's equal to, we get the negative natural log of the absolute value of cosine of x plus c. You probably should memorize this. We'll point out there's an alternative way of writing this answer. You can also equivalently write it as the positive natural log of the absolute value of secant of x, which is kind of funky, but it's true. I'll just write it up here. So just as the, right, you have the -1 times the natural log of the absolute value of cosine of x. That's equal to the natural log of the absolute value of cosine of x raised to the -1 power. But cosine to the -1, aka the reciprocal of cosine, is secant. So this is really the natural log of 1 over the absolute value of cosine of x, but that's the same as the natural log of the absolute value of secant of x. You don't need to know or to do it one way versus the other. I'm just pointing out that sometimes people write it like that instead of like that. So just so you're aware. Sorry, I got here a little late, but why did we choose cosine for u? Well, we chose u for cosine for 2 reasons. One, because its derivative is negative sine, but more importantly, we didn't choose u equal to sine because even though the derivative of sine is cosine, we don't have a cosine of x times dx in our integral. We have a 1 over cosine of x times dx. But yeah, we're trying to pick u. If we're thinking u substitution, which again, it's not always u substitution, but it's often u substitution. If we're trying to pick u, we want to pick a u that's stuck somewhere whose derivative is also there. So in the same sort of way, if we were going to try to integrate cotangent, first by rewriting it as the integral of cosine of x over sine of x. Now what's the better choice for you? Should I be picking u equal to cosine or should I be picking u equal to sine? Right. We're going to pick u equal to sine of x because it meets all the reasons we want to pick our u. It's stuck in the denominator. And importantly, its derivative is also there. Oops, I wrote it wrong. I wrote du equals sine of x. That's not right. Du is cosine of x times dx. And again, I can't emphasize enough, I'm gonna write it over here. If instead we had tried picking u equal to cosine, not really caring about the minus sign, but the derivative of cosine of x is negative sine of x and times dx. And I can't stress enough, this integral does not have a sine of x times dx. In fact, if you try to do the thing where you solve for dx and you got du divided by negative sine of x equals dx and then replaced in your integral, you'd have some serious problems. Because you'd have cosine of x over sine of x times du over negative sine of x. And that sign is not canceling out. Whereas if we do it the other way, like if you do the thing, again, not my personal preference, but if you do the thing where you let here du divided by cosine of x equal to dx and start replacing things, this integral is going to become the integral of cosine of x over sine of x times du over cosine. And oh yeah, the cosine of x over cosine of x, those divide to 1. And then you're left with du over sine of x, but sine of x is equal to u. So I can totally replace all of my x's with u's. And then we can integrate. So really, 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 you have to pick the thing so that the derivative also shows up. And I know it looks like the derivative of cosine is showing up as sine, but we don't really have a sine. We have a 1 over sine, which is not sine. 1 over sine is what? What's another name for 1 over sine? Sure, in this problem, yeah, but I meant more generally trig function wise, just like cosine is, or secant is 1 over cosine, cosecant is 1 over sine. So really, you can think of this integral as cosine times cosecant, which is weird. Anyway, doing this, integral of 1 over u is the natural log of the absolute value of u plus c, and then plugging back in that u is equal to sine, we get the natural log of the absolute value of sine of x. Let's see. Cool. There isn't really an alternative way of writing this integral. If you really wanted to make it work, you could write this as the negative natural log of the opposite value of cosecant of x. Nobody ever writes it that way. All right, so we know how to integrate 4 of the trig functions: sine, cosine, tangent, and cotangent. There's 2 left, and we're going to talk about them. They're not terrible. Well, they're kind of terrible. I don't know what your teacher's expectations are as far as memorizing these. I would suggest you memorize them, but that doesn't mean you have to. By the way, this is section 8.5 in your textbook, in case you're curious. So let's talk about the integral of secant of x. There's a really big story to the integral of secant of x, as far as how people figured out what it was. It actually has to do with map projections. So like, you know how like if you look at a map, it's not like to scale everywhere because the further you get from the middle, like things are like way out of whack and Greenland looks huge. If you project the globe onto a plane, the difference in like how much you're off by has to do with finding the integral of secant. It's kind of cool. It's really neat. It's just really neat. And the way you find the integral of secant is requires partial fractions, which we will talk about later. If you really are curious, sometime we can talk about how to find the integral of secant the long way. But the shortcut way that someone discovered after they found the answer was you can just multiply the top of this by, so be careful here, multiply the top and bottom by secant of x plus tangent of x. Which feels like it comes out of nowhere. It doesn't come out of nowhere, but just the story of where it comes from is a long story. So then we're going to multiply at the top. We're going to get the integral on top. So secant times secant is secant squared. And secant times tangent is secant x tangent x. On the bottom, we're going to write secant x plus tangent x. And I'm going to rewrite this just slightly to make it a little bit easier to see what's going to happen. I'm just going to change the order of addition on top. So I really want to write this as the integral of secant of x times tangent of x plus secant squared x all over, still the same order on the bottom, secant x plus tangent x. This isn't really necessary. It's just going to make it slightly easier to see what's going to happen here. All right, we're going to make a choice for a u substitution. You know we're going to pick u equal to? Well, the thing that's stuck somewhere. So what's stuck? No, I would argue or say blatantly, the top is almost never considered to be stuck. Like the thing in the numerator is not the stuck thing. Right. Yeah, yeah. So because really like just I want to it's not on this piece of paper. Like for example, if you have something like 2x over x squared plus 3, you can write this as 2x times x squared plus 3 to what power? Right. Oh, look, you got some stuff that's stuck being raised to some power. That's the way you might want to consider it. But back to this problem here. Usually, if you don't have a good intuition about what to do, picking u to be within the denominator is a nice place to try. So if we pick u equal to secant of x plus tangent of x, what's the derivative of secant? It's secant of x times tangent of x. What's the derivative of tangent of x? Oh, look, our du is exactly the numerator. Secant x tangent x plus secant squared x. How convenient. So what this means is we can rewrite our integral as, well, look, there's du on top. There's u on the bottom. And I think we've seen the integral of du over u enough times now that we don't need to write it as 1 over u times du. The integral of du over u is going to be the natural log of the absolute value of u plus c. And then we can rewrite that as the natural log of what our u was, which was secant of x plus tangent of x plus c. So the antiderivative of secant of x is the natural log of secant of x plus tangent of x. Now, kind of like how there's a nice pattern with trig derivatives, there's a nice pattern with trig antiderivatives. Meaning, so I know I said before, the derivative of secant is secant times tangent, and then if you take the derivative of cosecant, you get cosecant times cotangent with a negative sign in front. You can almost make the same sort of thing here. The antiderivative of secant is the natural log of secant plus tangent. The antiderivative of cosecant of x, you might guess would be the natural log of what? Instead of secant being secant plus tangent, we're going to have cosecant being exactly the natural log of cosecant of x plus cotangent of x. But just like with the cofunctions, you need to slap on a minus sign in front. Totally works. It also works with the tangent and the cotangent when we did, right? The antiderivative of cotangent. Well, yeah, this is where we don't need to get too crazy, James. Okay. I will also mention, because sometimes people do this weirdly, this is actually also equal to the positive natural log of the absolute value of cosecant of x minus cotangent of x. I don't know which way your teacher decided to write it in class. If they wrote it in class, both of these are perfectly acceptable. It's kind of super funky, but basically what happens is if you bring this -1 up as the power here, and then write this as 1 over cosecant plus cotangent, you can do some trig identities magic and turn it into cosecant minus cotangent. I'm happy to show you that in office hours. It's not super important though. Just pick which one you want to memorize if you're gonna. I would do the first one personally. I think the first one makes more sense to me pattern wise, but that's what I'm saying. So, brief recap here. All the trig things we want to know. All the trig things we want to know. Okay, so here they are. The antiderivative of sine of x is negative cosine of x. The antiderivative of cosine of x is sine of x. The antiderivative of tangent of x is the negative natural log of the absolute value of cosine of x. I should be throwing in some plus c's here. Or the natural log of the absolute value of secant of x. The integral of cotangent of x is the positive natural log of the absolute value of sine of x. the antiderivative of secant of x. Sorry, I like parentheses around my x's. Is equal to the natural log of the absolute value of secant of x plus tangent of x. I wish they wrote it as tangent plus secant, so that my plus and my t don't look too, like, I really feel like I have to really differentiate between my plus sign and my t, the tangent there. Oh, well, and then finally, the integral of cosecant of x is the negative natural log of the absolute value of cosecant of x plus cotangent of x plus c. Or, if you're spicy, the positive natural log of cosecant of x minus cotangent of x plus c. And then just to be extra complete about this, there's also four other things, right? The four other derivatives you should know, right? The integral of secant squared x dx is tangent of x plus c. The integral of cosecant squared x dx is negative cotangent of x plus c. The integral of secant x tangent x dx is secant of x plus c. And the integral of cosecant, I always mess up when I'm trying to write cosecant for some reason. Cosecant x cotangent x dx is negative cosecant of x. Let's see. Those are all the trig antiderivatives one could expect to possibly have to know. Without doing some, so these are all the ones you could possibly expect to have to know without like doing something to find them. And again, technically, I would say for cotangent and tangent, you could easily find those by doing U substitution relatively easily. The rest of them, not so much. Like, I don't think anyone wants or expects you to see the integral of secant and then multiply the top and bottom by secant plus tangent. No one wants you to do all this work. They want you to just know the integral of secant is the natural log of the absolute value of secant plus tangent. Okay, so last thing I'll say about trig for now is then there's U substitution type things. So for example, someone could ask, and I don't know if we've gotten here yet, because sometimes people do 8.5 like split into two sections. Someone could ask you like, what's the integral of secant cubed x tangent? How complicated do I want to get here? Not that complicated. Tangent x dx. So typically when you have sines and cosines, or secants and tangents, or cosecants and cotangents, although no one ever really uses cosecants and cotangents, your usual method of attack is to do a U sub by letting either U equal secant or U equal tangent. Or if it's sine and cosine, let U equal sine or U equals cosine. Which one do you pick? Good question. Well, let's see what happens if we pick U equal to tangent. What's the derivative of tangent? Secant squared. Do I have a secant squared? Yes, I do. But is it what I really want? No, it's not, because here's what happens. If you try to break off a secant squared from secant cubed, you're left with a secant of x times a tangent of x times the secant squared x that you pulled off. So great. Secant squared is all well and good. That's my du. Tangent, cool. Tangent's u. But the leftover secant is problematic. I can't do anything with that. If it was secant squared, I'd be in a good spot. Because I had the secant squared left over, there's a trig identity for secant squared. Oh, have we learned this trig identity? It's my favorite. You've probably heard me say it before if you've ever been in one of my classes. I tan and get sexy. 1 plus tangent squared x equals secant squared x. I tan and get sexy. So if that was secant squared, I would be in a good spot because I could replace secant squared with 1 plus tangent squared, and then tangent would be u. So it'd really be 1 plus u squared. But I just have secant, that's not helpful. So this is probably the wrong choice. Instead, we should have tried letting u equal secant of x. If u equals secant of x, then du is going to be the derivative, which is secant of x times tangent of x dx. I can take my integral. And again, I'm really of the mind, I really prefer to break off the piece I have. Right? Again, if you like, or if your teacher likes, you can do the thing where you say dx equals du divided by that and then cancel stuff. I think it's nicer to say, I have what I want. Secant cubed x is really secant squared x times secant x. And then I have that tangent x dx. And then I can see that the secant x times tangent x times dx, that's my du. And then the secant squared, since u is equal to secant, that's just going to equal u squared. So then I have the integral of u squared times du, which is going to be u cubed over 3 plus c, which is going to be secant cubed x over 3 plus c. Yeah.
Did you do the other way?
When you say the other way, what do you mean? Oh, yeah. Sure, let me actually do another, let me do a different problem with the other way. But yeah, we will do it that way. So let's say we had, yeah, we'll change it up a tiny bit. Let's see. Yeah, let's do that. Let's do, sorry, I'm trying to make it so we have to work a little bit harder here. Let's say we have the integral of, I want all even powers. Let's say we have the integral of secant to the 4th x times tangent squared x dx. And I don't know how into this particular topic your teacher is going to get, but here's the general kind of idea. When you've got sines and cosines, or secants and tangents, or cosecants and cotangents, you want to do a u sub. And you want to make a choice for u so that after you've dealt with du, you have an even power left over of your not u choice. Let me show you in practice what I mean by this. So let's make the wrong choice here. The wrong choice here is going to be letting u equal to secant of x. And I'm going to do it the other way. And so let's see why it's the wrong choice. So du is going to be secant x times tangent x times dx. I could write it larger. So then rewriting this integral in the way that has been requested, we're going to write this as secant to the 4th x times tangent squared x. Oh, I should actually do the solving for dx here though. Yeah. So then du over secant x tangent x equals dx. And then we have times du over secant x tangent x. And now I'm going to cancel some stuff, right? So secant to the 4th over secant, I can cancel one secant. Similarly, I can cancel one tangent. So I'm left with, and this is where things are going to be problematic, the integral of secant cubed x times tangent x du. Okay, I let u equal secant, right? Right. So my non-u thing is what? There's only one other thing. It's either tangent. And what's my power on tangent now that I've dealt with my du dx thing? The power on tangent is 1. The power on tangent is odd, and that's a problem. So whenever you're doing this thing, you always want to have an even power left over of your other choice. So the thing I didn't pick for you, if there's any leftovers of it, it needs to be an even power. Because if that was tangent squared, I could say that tangent squared equals secant squared minus 1. And then do it, oh my gosh, use that tree identity to help get me there. So let's do the right thing now. The right choice would have been to let u equal tangent of x. And my du is going to equal secant squared x dx. Solving for dx, du divided by secant squared x is equal to dx. Okay, so rewriting the integral of secant to the 4th x times tangent squared x dx as the integral of secant to the 4th x times tangent squared x times du divided by secant squared x. Okay, so now cancel appropriately. Secant to the fourth divided by secant squared is going to leave me with a secant squared. And then the not u thing, so the thing I didn't pick for u was secant, and I have a secant squared left over. That's a good thing. If I have an even power of my trig function that I didn't pick for u left over, I can make that work because 1 plus tangent squared x is equal to secant squared x. But u is equal to tangent. So really what I'm saying is 1 plus u squared is equal to secant squared x. So then I can rewrite this integral as, well, secant squared is just u squared. Sorry, whoa. Secant squared is what? 1 plus u squared. Sorry about that. Yes.
How come like why is the secant to the fourth x still there?
Well, sorry, so when rewriting this, I cancel the secant squared and secant. So really I'm writing this as the integral of secant squared x tangent squared x.
Right, but when you think
Mm-hmm.
and then when like u times du, so x times du over secant squared, and then like
Whoa, so let's see. So when I'm doing this, if I'm doing it the way you said I should do it, I'm gonna just take dx and replace dx with what it's equal to. And dx, right? So u is tangent, du, the derivative of u is secant squared x times dx. Right? The derivative of tangent is secant squared. And then I said, oh, I'm gonna isolate dx. So dx is equal to du divided by secant squared. So then I went back to my integral and I took my dx and I just replaced it with du over secant squared. Then secant to the fourth divided by secant squared is secant squared. And now I'm replacing secant squared with 1 plus tangent squared. But that's really 1 plus u squared because tangent is equal to u in this situation here.
Could you not do the other way?
What do you mean the other way?
Could you do the like u times du and then like tangent?
Where am I getting the u times du from?
Like, because isn't u substitution the integral of u times?
Not necessarily. It could be the integral of whatever in terms of u. Right? You could be like we've done, right? A lot of times we've gotten 1 over u times du. So really the thing you're integrating ends up usually just being some powers of u times du. But really it's not just u du. It could be u squared du. It could be u to the fourth plus u, right? It could be really anything. So here, I'm just trying to replace things with what I know they're equal to. I know that secant squared is equal to 1 plus u squared. And I know that tangent squared, well, since u is equal to tangent, u squared is equal to tangent squared. So tangent squared is going to be u squared. So when I replace each thing with what it's equal to in terms of u, I get 1 plus u squared times u squared times du. And then before I can anti-differentiate, I have to distribute that u squared and get the integral of u squared plus u to the fourth du. And then if I anti-differentiate those things, I get u cubed over 3 plus u to the fifth over 5 plus c. And then if I plug back in the fact that u is equal to tangent, I end up with, hope I can fit this in here, tangent cubed x over 3 plus tangent to the fifth x over 5 plus c. And again, I don't know how much of this your teachers are actually expecting you to do or are showing you, but it is something that does come up in section 8.5. So here's a couple examples of it. And now let's move on to other things. Other things. Yeah, what kind of other things have I got here? So many other things, sure. Let's do a couple of those and then we'll do that. Yeah, all right. Okay, let's do, some people had asked about polynomial long division as well. And how do you know like when you do it? So let's say we have something like this. Say we have, we'll do two of those. Yeah, let's say we have something like this first. Let's do the integral of, yeah, that'd be fine, sure. We'll do 3x squared plus 5x minus 7 over x squared plus 2x plus 1. So if it doesn't look like there's a likely u substitution, which it really doesn't here, letting u equal the bottom is not going to help me out. And the degree on top is bigger than or equal to the degree on the bottom, we can try polynomial long division. So here, we're going to do 3x squared plus 5x minus 7 divided by x squared plus 2x plus 1. And this is going to be a relatively straightforward thing in that it's only going to be one step. What do you multiply by x squared to get 3x squared? 3. And then 3 times x squared is 3x squared. 3 times 2x is 6x. 3 times 1 is 3. Forgot I made this problem harder than I meant to, but oh well, it'll be fine. Subtract 3x squared minus 3x squared is 0. 5x minus 6x is negative x. And negative 7 minus 3 is negative 10. So then we're going to rewrite this integral as the integral of the quotient 3 plus the remainder negative x minus 10 over the denominator or the divisor. Yeah, I made this problem harder than I meant to. But it's not, this problem is not undoable, so we should do it. I'm trying to decide which way I want to do it. Sure. Yeah, it's a better way to do this. Sorry, this problem's kind of gross either way. So here's what I would say. This problem, we have to recognize that the denominator does factor. So I'm gonna break this up into two integrals and watch this for a second here. All right, this is the integral of 3. And then I'm gonna factor out a minus 1 from the top here and write it as minus the integral of x plus 10 over x plus 1 squared. Just to not have to deal with the minus signs. And I factor the denominator. And then I'm actually going to break this up into two separate integrals. So I'm going to write this as the integral of 3 minus the integral of x over x plus 1 squared minus the integral of 10 over x plus 1 squared. Okay, let's deal with each of these separately. So the integral of 3 dx is just 3x plus c, I guess. I don't feel like I need that on that side really. And then the reason I'm doing these piecewise is because one of the pieces is going to be kind of gross. The integral of 10 over x plus 1 squared, I want to think of as the integral of 10 times x plus 1 to the negative second. We could do a u sub here, but it's a short enough u sub that I feel like we don't really need to. I'm going to say that that's 10 times x plus 1 to the negative 1 over negative 1. Because if you took the derivative of that, the derivative of x plus 1 to the negative 1 is negative 1 times x plus 1 to the negative second. And then the chain rule, you'd multiply by the derivative of the inside, but that's just 1. So this works. And finally, the part that's a little more challenging, let's see what's in the chat here. No, yeah, typically so a more general answer to your question of would they ask you to find the polynomial long division or do you have to figure it out on your own is most of the time when people are asking you test questions like this, they're usually not telling you what method to use. They're not telling you to divide or do a u sub or integration by parts or whatever. They're just saying, here's an integral, anti-differentiated. I'm not going to tell you how. That's part of the hard part about integration. So yeah, I wouldn't expect someone to tell you to use long division. This last part here, so we did the first part, we did the third part. Now I have to figure out this part, and this part is a little bit dicey. So for the integral of x over x plus 1 squared, here we are going to let u equal what's inside the denominator squared. So we're going to let u equal x plus 1. And then du is equal to just dx. So I'm always going to make sure that I transform whatever dx is into whatever it's equal to in terms of du. Here it's just a straight up 1-for-1. Dx turns into du because dx is equal to du. So when I start rewriting this, it's going to equal dx becomes du. And then the x plus 1 squared in the denominator is going to be u squared. And then I still have an x left over in the numerator, which is problematic. I don't want x's and u's. So what do? I solve for x. I say, oh, u minus 1 is equal to x, and I do what's called a back substitution. Any leftover x's, you solve for x and you sub for it back in for them. This is going to equal the integral of u minus 1 over u squared. And then we divide each of the things in the numerator by u squared. So you're going to have u divided by u squared, which is 1 over u, and 1 divided by u squared, which I would probably write as the integral of 1 over u minus u to the negative 2. The antiderivative of 1 over u is the natural log of the absolute value of u. The antiderivative of u to the negative second is u to the negative first divided by negative 1. And then finally, I would probably rewrite this as the natural log of the absolute value of u plus 1 over u, and then finally plugging back in x plus 1. It's the natural log of the absolute value of x plus 1 plus 1 over x plus 1. So my final answer would be all three of these pieces added together. So it'd be, I think, yeah, I'm just gonna write it down here. We'll use a whole piece of paper. So the integral of 3 dx minus the integral of x over x plus 1 squared dx minus the integral of 10 over x plus 1 squared is equal to 3x minus the thing we just found, which was the natural log of the absolute value of x plus 1 plus 1 over x plus 1 minus the integral of 10 over x plus 1 squared, which was 10 times x plus 1 to the negative first over minus 1 plus c. And if you don't love the way that's written, you're not alone. I would have to rewrite it as 3x minus the natural log of the absolute value of x plus 1 minus 1 over x plus 1. And then this part here would end up being a minus minus, so plus, and I would write this as 10 over x plus 1. Let's see. And I guess if you really, really wanted to, you could combine these last two pieces and say that's really 9 over x plus 1, but we don't need to do that. Okay. So polynomial long division clearly can be kind of a giant pain. Let's do one more example. Usually they're not, so I will admit that the part of the reason that problem was such a pain is because I didn't think super clearly about all the implications of what I was doing when I asked that problem. So let's look at one that's a little bit less terrible. Something, you're always welcome, Nikki. Let's look at something like, sure, 2x cubed plus 5x plus 7 over, let's not get too wild here. Let's say x minus 2. So here's a situation where we definitely want to use polynomial long division. The degree on top is, I should say, letting u equal x minus 2 as a u sub, not a good thing to start. Not going to work out. Right? Your du is going to be dx. That's actually not entirely true. You could totally do it that way. So let me point out, you could let u equal x minus 2 and do a u sub with a back sub. Nobody prefers to do not someone probably prefers it. But here's what I mean. If you let u equal x minus 2, your du is dx. So rewriting this, just watch for a second. I would get du equal to dx. My denominator would be u. And then the numerator, I could solve for x and do a back sub and say, okay, u plus 2 cubed plus 5 times u plus 2 plus 7. And then you'd have to multiply it all out and then divide each thing by u. And not that it's not doable, it's just not wonderful. Or I think it's better to do the polynomial division here. Let's see. I suppose if you didn't remember polynomial division very well, doing it this way might be preferable. But instead, we're going to divide x minus 2. Now watch this one thing. Our divisor is 2, divisor, dividend? I remember the terminology. 2x cubed plus, I really want to write a 0x squared there. Plus 5x plus 7. So x times 2x squared will give me 2x cubed. We multiply. You get 2x cubed, and 2x squared times negative 2 is minus 4x squared. Subtract. 2x cubed minus 2x cubed is 0. 0x squared minus 4x squared is positive 4x squared. Bring down the next thing. Repeat the process. What do you multiply by x to get 4x squared? 4x. 4x times x is 4x squared. 4x times negative 2 is negative 8x. Subtract. 4x squared minus 4x squared is 0. 5x minus 8x is 5x plus 8x, which is 13x. Bring down the 7, repeat the process. X times 13 will give me 13x. And then 13 times negative 2 is negative 26. Subtract. 13 minus 13 is 0. 7 minus 26 is 7 plus 26, which is 33. So here's what we can do. We can use another piece of paper because I don't have enough room. We can rewrite our integral of 2x cubed plus 5x plus 7 over x minus 2 as the integral of the quotient 2x squared plus 4x plus 13 plus the remainder divided by the divisor. And to me, that seems less terrible algebra to have to deal with. I think this division is less terrible than multiplying this all out. And then we can anti-differentiate. We're going to get 2x to the third over 3 plus 4x squared over 2 plus 13x. And then the integral of 33 times 1 over x minus 2 is 33 times the natural log of the absolute value of x minus 2. Okay. Let's go that way. One thing. The U substitution is going to be with you for the rest of your 16B, probably 16C career. Like if you take 16C. Oh, speaking of 16C, there is a co-class next. So I posted an announcement, but just in case you missed it, there is a co-class for 16C next quarter. It's on, like if you look at the announcements in Canvas, it's definitely posted on there with the time and the place and the CRN if you want to register for it, or if you don't want to register for it, that's also totally fine. You can sign up using the Google form and that becomes available. But just make sure, well, I mean, you don't really have to say, if you want to come to class when class happens live, make sure you leave that spot open in your schedule. I don't remember what time it's at. It might be Monday, Wednesday, Friday. It might be Tuesday, Thursday. I really don't remember what time it's at. So yeah, but go check out that announcement if you want to. So let's talk about more area between curve stuff. So last class we started to talk about the fundamental theorem of calculus. Again, let's point out that the fundamental theorem of calculus, technically fundamental theorem of calculus part 2. Let me just ask really quickly, actually, has anyone's teacher mentioned the fundamental theorem of calculus part 1, which has to do with taking the derivative of the integral? They usually don't cover it, but sometimes people do wacky things. So I just want to make sure no one's. I didn't see it in anyone's notes, but okay. Oh, let's see. Someone's in the chat though. Let's in the chat here. I think Lee has. Okay. All right. Well, we'll come around to that maybe. So, maybe not today though. More in the chat. Okay. He's talking about fundamental, well, but there's two parts of the fundamental theorem. So the part I'm specifically referring to is, has anyone done anything that looks wild like this? Like the derivative of the integral from 2 to x of sine of t squared dt. Does that look at all like something someone might have talked about? Where you have like an x up here? I'm seeing mostly no's. Evan, I'm hoping that's a no from you as well. Yeah, okay. Cool. That's fine. So if anyone sees something like this, let me know. We'll talk about it. But most of the time we kind of just skip this one. Yeah, it's there, but whatever. I'll just point out this is equal to sine of x squared. Basically, it's just saying the derivative of the integral just gets you back to the function you started with, which it should, because derivatives and antiderivatives undo each other. That's the whole point. That's why it's the fundamental theorem of calculus. But let's say we wanted to do something like we want to evaluate the definite integral from 0 to 3 of x squared minus 9 dx. So the nice thing about using the fundamental theorem of calculus is you don't have to be able to draw the region that you're talking about. You're talking about finding some area of some region, but you don't have to be able to actually see the region. So here's how we do it. We anti-differentiate. That's why we spent so much time practicing how to anti-differentiate functions, so that we can anti-differentiate this. You get x cubed over 3 minus 9x, and then you substitute in the limits of integration. Always the top one first, always the bottom one second. I would read this as the integral from 0 to 3, always from the lower to the upper. And if we plug in 3 first, you get 3 cubed over 3 minus 9 times 3. Minus, you plug in 0 second, and you get 0 cubed over 3 minus 9 times 0. A lot of the time when you plug in 0, you will get 0, but not always. Let's see, if we get this, we're going to have 3 cubed is 27 divided by 3 minus 9 times 3 is 27 minus 0. So we end up with 9 minus 27, which is negative 18. Negative 18. Why is our answer negative if we're talking about area? Well, because really when you're talking about these definite integrals, you're talking about the net area that's above the x-axis. And if you graph this function on this interval, y equal to x squared minus 9 is an upward opening parabola that's been shifted down 9 units. So when I graph this thing here, it looks like that. And specifically, when I'm going from x equals 0 to x equals 3, which is where this graph has an x-intercept, all this area is actually below the x-axis. So it's kind of getting counted as negative. And that's pretty typical. I would say you shouldn't really worry if your answer is negative if you're just doing a definite integral, but area that's below the x-axis ends up coming out as being a negative value, whereas area that's above the x-axis is counted as positive. Let's look at some more examples. Yeah, let's look at that. Sure. Let's look at, yeah, that's what I want. Yeah. The integral from 0 to 2 pi of sine of x dx. And actually, before we do this, let's graph it. So sine of x from 0 to 2 pi, one full period of the sine function. It's going to look like this. And it looks like there's just as much area that's getting counted as positive as there is that's getting counted as negative. So if you had to guess, what would you guess the definite integral is going to equal here? Well, yeah, the net area that's above the x-axis is there's just as much above as below, so they cancel each other out, and you're going to get 0. Let's actually do it though. If we anti-differentiate sine, we're gonna get negative cosine. Evaluated from 0 to 2 pi, you're gonna get negative cosine of 2 pi minus negative cosine of 0. What is cosine of 2 pi? It's 1. So you're gonna get negative 1 plus cosine of 0, which is also 1, and negative 1 plus 1 is 0. Everyone okay with those cosine values there? I know trig is always kind of like, but remember unit circle. This angle over here at the 0.10, the angle is 0 radians or 2 pi radians. So cosine of 2 pi is 1, and cosine of 0 is also 1. Also, it totally makes sense that these would cancel each other out because essentially you have negative cosine of an angle minus negative cosine of essentially the same, or the angle that's coterminal. So these values, right, this -1 here and this -1 here, -1 minus -1, of course they're going to cancel out. You have something minus the same something. Let's look at some area between curves, because that's really kind of where people like to go. So let's say we want to find the area between, oh, just covered up mine. Yeah. F of x equal to x squared minus 3x, and g of x equal to x. And we don't typically have to draw them, but it's nice to kind of draw them to see what's happening. So here's g of x equal to x. Nice and easy. And f of x equal to x squared minus 3x. If you factor on x for just a second, you can see that that's going to have x-intercepts at 0 and 3. If I draw my f of x, I'm going to have an x-intercept at 0, an x-intercept at 3, and it's going to be an upward opening parabola. It's going to look something like this. Somewhere up here, they'll intersect. Cool. Fine. So to be able to integrate this, we have to find where these functions intersect. So we're going to set f of x equal to g of x, which is going to be x squared minus 3x equal to x. And we're going to solve this in the usual way. We're going to bring everything to one side. You get x squared minus 4x equal to 0. Factor out an x. X times x minus 4 equals 0. So you either get x equal to 0 or x equal to 4. 0 is not surprisingly a point of intersection because we can see that they both go through the origin. And then this point over here of intersection is x is 4 and y is 4. And now if I want to find the area between these two curves, I'm trying to find all this area here. And the way we do that is by subtracting the top function minus the bottom function. So to find the area, it's going to be the integral from as far left as 0 to as far right as 4 of the top function minus the bottom function, which in this case is going to be, which function is the top function? G of x equal to x or f of x equal to x squared minus 3x? Yeah, g of x. Now, what if I didn't have the graph in front of me? How would I know which function was the top function? Here's what I would do. I would pick a point between 0 and 4, like 1. And I would say for x equal to 1, which function is bigger? Well, f of 1 is 1 squared minus 3 times 1, which is 1 minus 3, which is negative 2. And g of 1 is just 1. And 1 is clearly larger than negative 2. So that's a way you can tell which function is bigger on an interval without having to draw the graphs of the functions. So that's how we know that the top function is g and the bottom function is f. You make sure you throw parentheses around the one you're subtracting so that you know to distribute the minus sign. Simplify before we integrate. You're going to get the integral from 0 to 4 of x minus x squared minus 3x, so plus 3x. That's going to be x plus 3x is 4x minus x squared. And now we can go ahead and anti-differentiate. You're going to get 4x squared over 2 minus x cubed over 3 from 0 to 4. Plugging in 4, you get 4 times 4 squared over 2 minus 4 cubed over 3 minus, now plugging in 0. It is always worth checking, right? So a lot of the time when you plug in 0, you do get 0, but you should still check because it doesn't always happen. Specifically, cosine of 0 is 1, e to the 0 is 1. So when those functions are present, plugging in 0 will not typically yield 0. But here you plug in 0 and you get 0 minus 0. So this ends up equaling, let's see, I have 64 over 2 minus 64 over 3, which simplifies to 90. Yeah, what does it simplify to, James? I think it simplifies to 32 over 6. Seems right. Yeah, 32 over, no, sorry, 60, yeah. 32 over 3. Have your instructors talked at all about finding area integrating with respect to y or just with respect to x? Okay, that's pretty typical. We'll leave it at that then. Time is it here? Okay, I got a few minutes. Let's see. Oh yeah. We'll talk a little bit more about area between curves, but there's a couple of things I want you to see. So what if let's look at this example. Maybe, sorry. Let's say we want to find the integral from -2 to 2 of, let's do that. Let's do x cubed minus x. So let's actually just do it. So anti-differentiating, we're going to get x to the 4th over 4 minus x squared over 2 from -2 to 2. So when I plug in positive 2 first, I'm going to get 2 to the 4th over 4 minus 2 squared over 2. Minus, when I plug in -2, I'm going to get -2 to the 4th over 4 minus -2 squared over 2. Now watch me not simplify this all the way, but look at what I get here. 2 to the 4th is 2 times 2 times 2 times 2, which is 16. So I have 16 over 4 minus 4 over 2. Here's the part I really want you to see though. What's -2 to the 4th power? Well, 2 to the 4th is 2 times 2 times 2 times 2, which is 16. -2 to the 4th is -2 times -2 times -2 times -2, which is positive 16. What about over here? What's -2 squared? Look, this and this are the same. And if you have something minus the same something, what do you get? Yeah, it's not a trick question. It's definitely 0. 5 minus 5 is 0. 8 minus 8 is 0. X minus X is 0. Something minus the same something is 0. And here's a bigger picture. This function, y equals x cubed minus x, looks like this. I want to point out that the area to the right, which is all this, and this is getting counted as negative, exactly balances out with all the area to the left. It's going to be counted as negative. So look here real quickly. This section here is going to cancel out that section there. And this positive section here is going to cancel out that negative section there. And this is always true when you have an odd function. So more generally, if f of x is odd, meaning you got this rotational symmetry, then the integral from negative a to a, whatever a is, it could be 2 or 5 or 1,000 of f of x is always going to equal 0. Now, sometimes people ask questions like this on an exam, but in a very kind of challenging way. For example, I might ask you something like, what's the integral from negative 10 to 10 of x cubed over x to the 20th plus 1? And at least as far as I know, there isn't any way to integrate this. Like, I don't know how to find the antiderivative of x cubed over x to the 20th plus 1. But I don't need to, because there's a clue. The clue is that I've got negative 10 and 10 here, or negative 5 and 5, or these two numbers are opposites of each other. Those are opposites. It's a pretty good bet that this function is odd. But you typically have to show it's odd. So we need to show that f of x equal to x cubed over x to the 20th plus 1 is odd. I'll point out, looking back at the previous example for a second. In this previous example, I plotted some points that actually labeling them. If x is 2 and my function is x cubed minus x, 2 cubed minus 2 is 8 minus 2, which is 6. And if x is negative 2, negative 2 cubed minus negative 2 is negative 8 plus 2, which is negative 6. The thing that you have to see about odd functions is that when you plug in the opposite value of x, you get the opposite value of y. So to check that a function is odd, we need to show that f of negative x is equal to negative f of x. That's how you show a function's odd. And that plugging in the opposite x value, you get to the opposite y value. So let's do it. So f of negative x is negative x quantity cubed over negative x quantity to the 20th plus 1. A negative thing to an odd power stays negative. Negative times a negative times a negative is negative. Negative thing to an even power doesn't stay negative. Negative x times negative x is positive x squared. So negative x times negative x 20 times is going to be positive x to the 20th power. But look, actually, let me do it this way. Negative f of x is negative 1 times the function f of x. Now I want to be extra careful here. When you have negative 1 times a fraction, we do not multiply it to the top and the bottom. Because multiplying by negative 1 over negative 1 would actually be multiplying by positive 1. Really, I have negative 1 over 1. So I'm going to multiply the negative 1 to the top and just positive 1 to the bottom. And oh, look, those are the same. So this shows us that f of negative x is equal to negative f of x. So f of x is odd. Which means that this integral here is equal to 0. Because the area on the right and the area on the left would exactly cancel each other out. Yeah.
Is it 0 when the numbers are the same?
Yeah, so the number, right, like if it was -2 to +5, no dice. They have to be the opposites of each other. There's a less useful, but still slightly useful thing that's true about limits of integration like this when the function is even. But less useful. So here's what's true. So for an odd function, the integral from negative a to a is 0. On the other hand, if your function is even, which means that plugging in the opposite x value still gets you the same y value. So f of negative x is equal to f of x. The example you should think about is like f of x equal to x squared plus 1. Think about that parabola. That parabola is an even function, has symmetry about the y-axis. Then the integral from negative a to a of f of x is equal to twice the integral from 0 to a of f of x. This is not nearly as useful. You still have to actually do work to find the answer, but let me point out why it's kind of useful. So let's say I wanted to find, I want to find the integral from -3 to 3 of, let's be sure, of x squared, well, let's say, 3x squared plus 10x to the 4th. Which is definitely an even function. How do I know it's even? Let's check it out. F of x, I mean, I know this one's even because it's a polynomial with all even powers, but all even powers doesn't necessarily mean even or odd. So we have to check. Our function is 3x squared plus 10x to the 4th. So f of negative x is 3 times negative x squared plus 10 times negative x to the 4th. But negative x times negative x is positive x squared. And negative x times negative x times negative x times negative x is positive x to the 4th. So f of negative x is indeed equal to f of x. So it's even. Here's why this is semi-useful. Watch this for a second. If I do this integral this way, I'm going to get x cubed plus 10x to the 5th over 5, which is 2x to the 5th, evaluated from -3 to 3. And then I plug in 3, and I get 3 cubed plus 2 times 3 to the 5th. I didn't really think about how big that number was going to be. Minus, plug in -3, -3 cubed plus 2 times -3 to the 5th. And it's just kind of gross, right? Like, okay, 3 cubed is 27 plus 2, 3 to the 5th is 243. Minus, and then you've got, right? It's just, it's a recipe for making mistakes. On the other hand, we could have said it's going to equal 2 times the integral from 0 to 3 of 3x squared plus 10x to the 4th. And then it just becomes a little bit less work. That's going to be 2 times x cubed plus 2x to the 5th from 0 to 3. And then we're going to get 2 times 3 cubed plus 2 times 3 to the 5th. Oops, I forgot the 2 here. See, mistakes. Minus 0. Again, not a huge savings in work, but it does save you kind of the distress of maybe screwing up a minus sign over here. Either way, we should get whatever we get. 2 times 243 is 486. Plus 27 is 513. I picked not great numbers. I'm sorry about that. 1026. So odd functions certainly more useful when it comes to integration, but sometimes even functions show up and it is nice to be able to make it a little bit easier. A lot of times in textbooks or in solutions manuals, you'll see them jump from like this integral to 2 times this integral. But like, what are they doing? They're using the fact that it's an even function when they do that. Let's look at some more definite integrals. Yeah. Oh yeah, we should do we have time? Yeah, we have time. Let's do one more definite integral. So I want to say one thing. Yeah, let's do that. So let's say we want to find, so let's not drop all the papers everywhere. I want to find, how do I want to do this? Yeah, let's go that way. So I'm just trying to make sure this comes out not terribly. Sure, we'll do classic. The integral from 0 to 2 of x squared times the square root of x cubed plus 1. Which certainly looks like we might need to use what method of integration? What's the only method we've really got? Use substitution. I know you know it, you're just like, I don't want to say anything. Okay, so what's our choice for you here? I think there's one good choice. What is it? Exactly. The stuff that's stuck, the stuff whose derivative is also right there. Right, because again, I don't have exactly 3x squared dx, but close enough. Let me ask you both, do you prefer doing it the way where you divide to get dx by itself? Yeah, okay, that's it's fine either way. So doing it that way, I have du divided by 3x squared equal to dx. So I'm going to rewrite this as, so when it's definite like this, I'm going to tell you what to do, but we're just going to wait a minute. So we're just going to leave the limits of integration off for a second. So it's going to be x squared times the square root of x cubed plus 1 times du over 3x squared. And immediately we want the thing down here to cancel out, and it does. So then I would bring out the 1/3. I would have the square root of x cubed plus 1 becomes u du. Now, here's where you have a choice. You could make what I would consider to be the less good choice and leave your limits of integration as they were. So in the beginning here, this is from x equals 0 to x equals 2. And you could keep it that way the whole way. And if you do it this way, you have to then switch back to x when you're done with this problem. So let's finish this out. We're going to get 1/3 the integral from x equals 0 to x equals 2, u to the 1/2 du. You do need to write x equals though to indicate to the person that you know that these are still x's where this is a u. We integrate, we get 1/3. The integral of u to the 1/2 is u to the 3/2 divided by 3/2 or times 2/3 from x equals 0 to x equals 2. We then multiply 1/3 times 2/3 to get 2/9. We plug back in the fact that u is equal to x cubed plus 1. And now we can plug in x equal to 0 and x equal to 2. Although 2 first, 0 second. We plug in and we get 2/9 times 2 cubed plus 1 to the 3/2 minus 2/9 times 0 cubed plus 1 to 3/2. And simplifying, we have 2/9 times 8 plus 1 is 9 to 3/2, and 0 plus 1 is 0. Sorry, what did I just say? 0 plus 1 is what? 0 plus 1 is 1. 9 to the 3/2 power is the square root of 9 cubed, which is 3 cubed, which is 27. So we end up with 2/9 times 27 minus 2/9 times 1. And factoring out the 2/9, you get 2/9 times 27 minus 1, which is 26. So you end up with 52/9. And this is not the way I would encourage you to do it, although it's totally fine. The other way, which I think is better, is instead to switch things to be in terms of u. Meaning, when I get to this integral over here, instead of writing 1/3 the integral from x equals 0 to x equals 2 of the square root of u, I would really rather rewrite this as 1/3 the integral from u equals something to u equals something of u to the 1/2. I know we're out of time, but give me just a minute. So let me ask you all. If x equals 0, what does u equal? Well, plug in 0 for x, what do you get for u? Right. 0 cubed plus 1 is 1. And if x equals 2, then u is going to equal 2 cubed plus 1, which is 8 plus 1, which is 9. And the nice thing about doing it this way is after you've anti-differentiated and gotten 1/3 times u to the 3/2 times 2/3 from u equals 1 to u equals 9, you don't have to switch back to x's because everything is in terms of u, including the limits of integration. So this 1/3 times 2/3 is 2/9. And then you plug in 9 for u and you get 9 to the 3/2 minus you plug in 1 for u and you get 1 to the 3/2. And look, that's exactly the same thing that I had right here. I think this is nicer, but either way is totally acceptable. And at the end of the day, we'd still have 2/9 times 27 minus 1, which ends up being 52 over 9. So when you have to do a u sub in a definite integral, you have the choice of keeping your limits of integration in terms of your original variable x, and then changing everything back to x before you plug in, or changing your limits of integration to be in terms of your new variable u, and then you don't change back to x at the end. You just say, oh, this is what my u's are. Either way is fine. I will tend to do it this way though. All right, it's 11:52. I should stop talking.